All right, it's time to start our last section relative to mass moment of inertia, and that involves integration methods. So what all have we accomplished? We've done area moment of inertia, introduced the concept, we did it by composite parts, we looked at the integration. Then we introduced mass moment of inertia, we did it by composite parts, and now we're going to do it by integration. So this chapter of just moment of inertia has 6 sections. There's a lot here. So we're starting the last section. So integration methods. All right. So let's just think what's involved here. And let me just remind us of what the equation for mass moment of inertia is. R squared dm. Say IZ. All right. So let's think what this means. Okay. When we go to format, it says the differential mass that we come up with has to all be at the same radius. Okay? Remember, when we had the other things in here, when we did center of mass, say, we had, and we had, say, a y out here, we had to come up with a differential mass where the whole mass was a distance y away. Now we need to come up with a mass where all of the mass is one distance r away. Well, how do you do that? Well, it's really quite simple. It says, here's a sheet. I'll let you see it kind of there. And we're just going to roll it up. And I'll let you look down it. Whoops. A little stubborn, but what I'm trying to create is a shell or a pipe. Okay? And the paper's really thin here. Okay? So basically all the mass is at one radius if I could form a perfect shell. All right? So this is what we do here is, so here's this axis Z, and we picture this thing wants to spin around it like so. Okay? And so what I'm going to do is create objects where I have a bunch of concentric shells. So here's one shell, and you can see it has this given thickness and it's dr, so it's really, 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 really thin. Okay, and it has a characteristic height. So relative to the axis I want to spin around, I'm going to have a whole bunch of shells where the shells get greater and greater and greater radius coming out, and to fit whatever the thing is I'm looking at, then the height can vary. Okay, so what I'm going to picture, basically making a whole bunch of bizarre shells and just expanding out to create them, to create the overall object. All right, if you're using a shell, let's think what the shell is made of. So this is, I'm showing thickness here, but it's really paper thin. All right, so what would be the volume of the shell? Well, the shell is just a piece of paper where we take the ends and bring them together. Okay? So if I look at, and here's the whole piece of paper, let you see that. All right. Their circumference was basically one dimension of the paper. Okay? So what is the volume of a piece of paper? Well, let's zoom out for a moment. The volume of a piece of paper would be this dimension times this dimension times the whatever that thickness is. It isn't very big. Okay? And then we take this and we join the ends together. Okay? So, getting so you can see the paper again real well. The differential volume is one length of the paper will be the circumference around here times the height and then times the thickness. That would give us the volume of the shell. Why did we look at getting the volume? Because then we multiply the volume by its respective density, we get mass, which is what we need right here. So this is the technique, and once again, there's two ways of doing it. We'll wind up showing you both ways, but here's the key. One of the ways is what's called the shell method. It's famous. People who've had this course 30 years later still remember going through and constructing these things. All right. So using a whole series of concentric cells to make up the device, all shell mass is at one radius. Okay, that's important, and that's required by the nature of this equation. Now, once again, we'll note we can do this another way, and that's expressed here. Summation of differential components where the differential component inertia is known. So what did we do before? We had little differential IXs. Here we're going to have differential IZs, and we'll simply add them up. We'll show you how that's done in a little bit. Taking a look at our first example, we've already looked at a disk. So here's a disk, radius r. Here's the xy plane. It's the idea is this would rotate about the x-axis in the usual way. It has a thickness t going down along the x-axis, and from what we've already done, we know this is 1/2 mr squared for Ix. So this is rotating about the x-axis. Its mass moment of inertia will be 1/2 mass times radius squared. We're going to prove that. Okay. So let's we're going to use a shell. So I disk relative to the x. Here's our integral r squared dm. So we're going to make a whole bunch of shells. Little one here and a bigger one and a bigger one until we get out to the outside. So the shell has thickness dy. So picture as this goes around, I have this axis here going up here so I can measure radius along the y. That works. Okay. So here's dy and r is equal to y. So if I do that, I'm going to be taking shells that start from the initial shells will have radius 0, and eventually they'll expand to radius r. I should make this a capital R, so you can relate to that. Okay? So I'm going to take the radius out along the y-axis, so y squared. Mass is density times differential volume. So we're going to use that same dV. So it's 2 pi r, where r is y. That's one dimension. Thickness, that's right here, and dy, the thickness of the shell. Do the integration. We wind up with this. Now that doesn't look like 1/2 mr squared, so what do we have to do then to figure this out? Well, we've got to compute the mass. So just to prove it, and I'll note that the disk mass would be density times area times thickness. So this is little r. We can, let's see, put a big capital R in here. Let's put a capital R in here. There we go. So rho pi r squared times thickness. Pi r squared times thickness is the volume times density. Gives us mass. So if I stick this into here, all right, 1/2 mass, that's the thing I just did, times radius squared. I'll make these big R's again. There. And we wind up with that. And they're the same. All right, we're going to stop right there. And next time we're going to start looking at some more complicated shapes. And we'll see 2 ways of doing the integration. See you next time.